Hi, my name is Lars Rönnbäck, and some of you may know me from my recent research in information modeling, but before that I did research in the foundations of mathematics. And today I want to talk to you about something close to my heart, and it's math and kids, and particularly how kids perceive numbers and how they learn to count. This is a presentation that I put together for the Ministry of Finance in Sweden when they held a day of talks around kids and economy. What I do other than this is that I have a small consultant company where I work with large-scale simulations, trying to predict the future at large companies in Sweden. So what then is research within the foundations of mathematics? Well, it's not just larger numbers and simple arithmetics. It's actually a rich field that is cross-disciplinary, and it involves set theory, number theory, logic, and even philosophy and psychology. And it's much more about how to build mathematics and how the mathematics that we have today is built. It involves things like usability, understandability, and universality of the things that you work with. Trying to get math to be as usable as possible, as simple to understand as possible, and as universally applicable as possible. When you build mathematics, there are a few things or a few simple rules that you adhere to when you build your math, and one of the most important concepts that you have in mathematics is the concept of stringency, which means that when you introduce new concepts in mathematics, it has to build upon that which you have already defined. The issue here is, of course, that if you compare this to say, a lexicon or a thesaurus, where you have words and their definitions. If you have a definition of a word, you will want to look up those words that constitute the definition. And when you look them up, they in turn have their definitions. And this, of course, becomes some sort of infinite loop. So it has to stop somewhere. And in mathematics, it stops with something that is called an axiom. It is supposed to be, anyway, a concept that is so obvious that its definition can be omitted. So axioms in mathematics are really obvious truths that you start with, sort of your building blocks that you build everything else in mathematics around. And that is great, of course. So every one of you can start building math if you want to. Let me show you the axioms that most of our current mathematics is actually built upon. They look like this. These are the axioms of Zermelo-Fraenkel. And as you can see, they're probably not that intuitive and self-explanatory to a non-mathematician. And even for mathematicians, they're quite hard to grasp. But even while they look like they do, there has to have been some sort of intuition behind each of these ones when they were created. So what I did when I did my research was to try to find the intuition behind the axioms that our current mathematics is built upon, and possibly find also different axioms that could be easier to understand on an intuitive level. So my work was focused on this simple idea that if an axiom is not simple enough to be understood by a child, it's actually not a good axiom. And that is where my research was focused. And that is how kids came into the picture. And thinking about children, I realized that most children and adults, they actually know how to count. But how is it then that so many seems to have forgotten how they learned to count? And the interesting aspect here is also that when you learn to count, you actually encounter a lot of concepts from higher mathematics that we later on completely forget that we actually know and mastered. Also, some find it actually very challenging to count. So could it be that the ones that find it challenging are missing some crucial pieces from these concepts of higher math that you learn along the way? So I started looking into what type of research was available around this area, and it turns out that there is actually quite a lot of research that has been done when it comes to kids counting and dyscalculia and things like this. So both international and Swedish initiatives that look into this, but I couldn't really find anything that actually brought this up in a step-by-step fashion, where you actually sort of in the axiomatic fashion start with something and look at the very first things you need to learn in order to reach the level where you can count, and you build upon that and see what's the next thing you need to learn, what's the next thing you need. So you get a complete picture of all the requirements necessary in order to be able to count. So I focused my research on that, and that ended up in a book a few years ago. So I've collected this work in a book that's called My Little Big Math Book. It's illustrated wonderfully by a talented woman named Lydia Steiner. So this is a book about a small girl and how she learns to count. And we will be looking at some pictures from the book in the rest of the presentation, and I will look at a few of the steps necessary in order to learn how to count, just so you can see the amazing amount of mathematics involved and the fantastic capabilities of kids when they actually learn how to count. Well, the first thing you need is to actually separate yourself from the rest of the world. And this is, of course, something that happens very early, maybe even as early as in the tummy. I don't know exactly when this happens, but this is a crucial moment when you realize that there is actually something else that is not myself. And we distinguish that this thing out there is something that we can start to observe and draw conclusions about. In logic, we talk about the existential qualifier, and this is sort of when you realize that you can start using this existential qualifier. So once the child has learned that there is something else, they also start to recognize that this else consists of a lot of different things. So they start to compartmentalize this else into different things, like the lamp, like a comforter, the bed. And looking at that differences, they are found by either things being in different locations, they can have different shapes or forms, people may name the things differently, they can come from different places, or they relate to other things in different ways. So there are many different types of ways that things can differ from each other. And this type of discernibility is something that kids learn very early on, to distinguish these differences in order to be able to find and compartmentalize things. So it will probably quite early on distinguish the table and the lamp, even though they are placed upon each other, that they are two different things. Now, knowing that there are different things, the next step is actually to be able to recognize that you've seen a thing before. So you can say that this is the same thing that I saw. It could be, for instance, your father and you recognize your father through his hair color, his face, his voice. So in order to do that, there are a few things that you require. You require a memory, so you can actually remember the features of your father. But it also requires the ability to be able to assign identities. So you have assigned an identity to this father thing. And what happens when you actually recollect your father is that you look at the properties, and the identity is sort of like a street address in your memory. So when you look at the houses on that address and you find the house that looks like your father, you find the identity and you realize that, yeah, this is my father, and you remember your father. An interesting question here is, of course, how much would your father have to change before you wouldn't recognize him again? Anyway, after a while, you can actually recall and remember a lot of different things. Looking at this child, you could see that there's a lot of toys in the bed, and the child is probably being able to experience all of these toys together as a set. And in this case, it could be the set of my toys. And the interesting thing here is it doesn't really matter if I were to shuffle the toys around in the bed, it would still be the set of my toys. This is precisely the definition of a set in mathematics. It's defined by its members, but it doesn't have a particular order to it. Now we can take that set of toys and start to play around with it. For example, if we divide it into heaps, it's quite easy to tell if there's more toys in one heap than in the other one. This is dependent, though, on the relative difference. Let's say, for example, that I have one pile that contains one orange and another pile that contains two oranges. It would be extremely easy for us to tell that there are more oranges in one pile than the other one. So the relative difference here is quite large. There's twice the amount of oranges in one pile, but the absolute difference is just one orange. If I create a pile of, say, 100 oranges in one pile and 101 oranges in the other pile, the absolute difference is still one orange, but the relative difference is now very small. It's just below 1%. So it would be extremely difficult to tell which of the piles is the larger one. So even if we don't know the exact numbers, the concept of fewer and greater is something that kids pick up quite early on. For example, you could often hear them say that, well, I got fewer candies than my little brother. So they keep count even if they don't know the exact numbers. Now, next, you also start to recognize as a kid that there are similarities between things. And the interesting thing is that we talked about differences before, but similarities are actually quite a lot more complex, because now we're talking about classifications here. And classification is a more abstract concept. So maybe you put all of your round things in one pile and stuff that is not round in another pile. Let's say again that you have some oranges and I have two round oranges. What happens if I step on an orange? Do you think it's still round? Should it belong in the set? This is actually a quite difficult question, but and two kids could quite possibly disagree whether to keep this flat orange in the set or not. As a mathematician, you try to shy away from vagueness in this sense, so you want precise definitions. So for a mathematician, there is a precise definition on how much I would have to step on this orange before it becomes flat and is no longer round. The good thing about having precise definitions is that you can always reach perfect agreement when you have them. But this is maybe something that kids don't do to that extent, but still they explore the possibilities. Now this gives the kids the ability to create sets from similarities or classifications, like the set of all round things, the set of all square things, the set of all green things, and so on. And you can actually see kids at a certain age explore these kinds of concepts when they are fiddling around and playing with their toys and piling them up in different piles like this. Once they have this, they have the basis of the set theory. So the next step is actually the first step when you start to count. And if you are going to start to count, the first thing you need to be able to count to is the number 1. And that also comes quite early, where they can actually tell the difference between the one and the many. And if you have a pile like this and you pick up one thing, there will still be many things left. The interesting experiment here is, of course, if you take one thing from a pile and put it in another pile, one thing at a time, you will at some point have reversed the starting position that you have. So now you have one thing left, and the other pile is the thing that has the many in them. Once you've learned to count to 1, the next thing is to familiarize yourself with 0 and everything. So if you pick up everything from a pile, the pile of course disappears, so there is nothing left. And now you're starting also to actually familiarize yourself with some simple arithmetics, like what's the addition. If you add 0 to something, it's a non-operation, it will still remain the same. And if you subtract a number with itself, then nothing will remain. So also here, another important thing is that when you talk about everything, everything is contextual. So it refers to some sort of context. I'm not talking about picking up everything and explicitly meaning everything in the whole world. You probably talk about everything in the context of your toys, or the context of the food on your plate, things like that. So everything is contextual, but it's often quite easy to understand which context and what everything actually refers to. So everything and nothing are two important concepts that you need to familiarize yourself with. So one thing you can do if you are faced with two piles of things that have almost the same number of things in them, so that the relative difference is small and it's hard to tell which one has the most things. What you can do is actually line these things up. So you take one thing from one pile and one thing from the other pile and put them in the same position next to each other, and then you continue to do so and line the things up. And this will actually tell you which of the piles are larger, because that line will be longer. So you cannot find a corresponding thing in the other pile once it's empty. So this is an algorithm that actually produces a mapping between the things in the piles, so you can tell which one has the most things in them. This is functions like this, or mappings in mathematics, are called bijections if they have the same number of things, and injections if the things are if they have different number of things in them. Lines can become quite long if you have a large number of things, And it's quite easy to recognize that a line is just one type of pattern. So what you can do is actually break the line and create some other types of patterns, like the eyes of a dice or something like that. And what patterns do is that they make it much easier to get the visual cues that you need in order to tell when something is larger than something else. And also, what could become difficult with these piles of things that you want to compare the numbers of is if they are quite large in size. So what you can do is take a bag of peas, for example, and for each thing in your pile, you grab a pea. And then you start to build patterns using the peas instead of using the actual things. The important realization here is that it doesn't really matter if you count the peas or if you count the actual things, since you've made this one-to-one mapping. So number is actually independent of what you're counting, if you have these one-to-one mappings between them. And this is an abstract concept to grasp. So once you have made that realization, you can actually start to assign some symbols to these patterns that you made. So if you have those lines, or if you have something that looks like the eyes of a dice, or something else, you can start to create these symbols that actually mean the same thing. So it could be the symbols or digits then from 0 to 10, or it could be the actual words. Each of these are actually just different conceptual representations of the same thing. So this is where you familiarize yourself with the actual numbers that you've before just had an abstract notion of. Now you're starting to get these concrete notion where what these patterns that you built are actually named. At this point, you're actually ready to start counting. So what you do when you count is actually that you word the name of the pattern as you are building it. So when you're building a pattern one piece at a time and actually wording 1, 2, 3, which is just the name of this pattern that you're currently looking at, you're actually counting. And this requires, as you saw, quite a lot of insights on the way. And of course, if you're sitting in a car or something and driving by houses in a street and you want to count how many houses there are, there's actually really no way that you can pick those houses and form patterns. So what do? Well, you don't have any peas in your car with you either. So one thing that you always have with you are your fingers. So your hand is a pattern as well. And you can start to do this one-to-one mapping, similar to what you did with the piece, but now you do it with your fingers. And you've learned that if one finger is extended, then it's 1, 2, 3, 4, 5. So this is actually why and how kids learn to count on their fingers. You get this one-to-one mapping between fingers and the thing that you want to count, but it's too difficult to actually place in a pattern by itself. A great way to introduce the number system is through the use of value. Before we had currencies, we needed to trade things in order to make exchanges, and things had different values. So the numbers didn't actually mean the same thing. For example, if you look at the picture, maybe the 4 oranges, the number 4 is equal in value to the number 1 when it comes to teddy bears. So I can trade 1 teddy bear for 4 oranges. So this type of trading actually introduces kids to the start of the number system, the realization that one number can be valued more than another number. Using this knowledge, it's possible to create price tags that have the values of oranges and teddy bears. So for example, I can say that my rabbit has the cost of 7 oranges. But of course, if I were just to use oranges, the price tags could become quite large after a while, extremely large if you want to sell something valuable. So it's easier to express that the price of the rabbit, rather than to write down 7 oranges, I say that it's 1 teddy bear and 3 oranges. And now you're very close to the actual number system that we have with the decimal positional system. The only difference being that we use the digits up to 9, and then when it overflows, we create another position that represents the number of tens, and then the number of hundreds, and so on. So this is also a great way for kids to familiarize themselves with the number system and how to express larger numbers the way we do it, even if we can start by doing it using simpler things than actual digits. So if you found this interesting, I really recommend buying the book, which has more of the same stuff. To the left here you see a list of the keywords of the things that you have to learn on your way to starting to count and understand the positional number system that we have. And as you can see, it's quite a lot of things, and many of these tie into concepts in higher mathematics, information modeling, psychology, philosophy, etc. So it's quite an interesting field, and it's fascinating to see how kids from their birth up to about their school age actually learn and master all these things. If you have any further questions, feel free to contact me on my email address. And with that, I'll say thank you.